All right. Good afternoon, everyone. Welcome. Thank you for joining us, and welcome to the Future of UV Advanced Manufacturing Trends, Strategies, and Applications, a regular webinar series presented by the State University of New York College of Environmental Science and Forestry in collaboration with RadTech International North America, the Association for UV and EV Technology. My name is Brandon Murphy, and I'll be your host today from SUNY ESF. As a reminder, all the webinars in this series are recorded and archived and posted at the address you see there, and you'll also get a reminder email at the end of this with that link, so don't worry about trying to jot that down. Just a reminder also, we have some upcoming webinars. So there's another webinar, Beyond Coating and Cure, the finer points of applying UV curable materials in your manufacturing process. That's going to be a number of presenters on December 12th. And then Mickey Fortune hasn't sent out the advertisement yet, but there's also going to be in early January one on the cationic cure process presented by Mike Idacavage. Also, as a reminder, SUNY ESF offers a fully online graduate certificate in radiation curing chemistry. There's two courses, the Introduction to Polymer Coatings and the Radiation Curing of Polymer Technologies, and you can find more information at our website or at the webinar website as well. And also, everybody's probably already all signed up, but the RadTech 2020 UV and EV Technology Conference is coming up March 9th through 11th at Disney in Orlando. There's still some exhibitor spots left available. Registration should open. You can register at radtech2020.com or find more information, or visit the RadTech website, radtech.org. So today's webinar on UV LED for wide web flexible packaging is going to be presented by Jennifer Heathcote of Eminence UV and Joe Spinnato of Ashland. Jennifer has been in the UV equipment and applications business since 1998. She's a technical and commercial advisor with Eminence UV and is considered a leading authority on both conventional UV and UV LED technology, as well as their use across a broad range of graphic and industrial curing applications. Jennifer earned her Bachelor's of Science in Mechanical Engineering from Purdue University and her MBA from the Fisher College of Business at Ohio State University. Joe is the food packaging manager for Ashland. His role is mainly focused on working with product and business development to design food packaging products, laminating adhesives and coatings, which will be safe and compliant for their intended use. In this role, Joe develops protocols for migration testing and assists Ashland's analytical services and technology with executing them. Additionally, he's involved in customer education in the areas of food packaging safety and regulation, and currently serves as a member of the Food Safety Alliance for Packaging, which is focused on food safety through the supply chain from chemical manufacturers, converters, and brand owners, and the Adhesive and Sealant Council Regulatory Affairs Committee. Prior to Ashland, Joe worked with Invista SARL on food packaging issues, filing food contact notifications with the FDA, product filings for Europe, the EFSA, South America through Mercosur, and developing a program for China's food packaging law. In addition to food packaging, Joe has worked as a toxicologist and performed hazard assessments for the EPA's Integrated Risk Information System, the IRIS system, FDA Center for Food Safety and Applied Nutrition, and several REACH consortia. His prior work has involved general toxicological support, new chemical registrations in the U.S. and TSCA, China, Australia, Canada, and Japan. He's also served on various chemical panels and trade organizations, like the American Chemists Council on Crystalline Silica Panel, Formaldehyde Council Institute Science and Regulatory Committee, and the National Stone, Sand, and Gravel Association's Environmental Safety and Health Committee. His undergraduate is in biology from Spring Hill College, and his doctorate is in pharmacology from the University of Louisville. And I thank you to both of you, and Jennifer is going to start us off today.
Welcome, everybody. We're excited that you are joining us today. I wanted to give a special thank you to Danny Bielman at the Flexible Packaging Association, who sent notice of this webinar out to the FPA members. So if you're joining us from FPA, a special welcome to you. When Ashland and I set out to do a webinar about 6 months ago, We wanted to do it on UV LED technology, and we wanted to do it on flexible packaging. But when we started looking at the market a little bit closer, it became very clear to us that the audience using narrow web presses is quite different from those using mid-web and wide web presses. The narrow web market's been exposed to LED technology for a good 10 years now, and so what they were looking for was a bit different to many mid and wide web who may not even be familiar with UV technology. So we actually ended up with 2 webinars. This webinar is more of an introduction to UV curing technology, as well as a better foundational overview of LED technology. And then Joe is going to provide some regulatory and migration information on UV curing as it relates to flexible packaging and food packaging. And then hopefully you will stay on until the very end, because the last 5 slides are going to really tie everything together. And these webinars are both archived, so if you then want to look at the narrow web webinar, which is going to go more into coatings and adhesives and a little bit of inks and a bit deeper on the LED technology, feel free to watch that at a later time, and you can certainly go back and forth if you want to revisit any of the material. So with that, I'll just kind of give you a brief overview of what we're going to talk about. I kind of mentioned it already, introduction to UV curing. For those of you who may be using water-based or solvent-based technology today and may not be familiar with UV technology. And then we'll continue on with the specifics of LED, as well as regulation, migration, testing, and then we'll recap at the very end with how all of this ties together. The benefits of UV curing for printing applications are quite extensive. And again, this slide is really for those of you who are more familiar with water-based and solvent-based printing. UV curing is an option that you have. It's a drying technology. It works with inks, coatings, and adhesives. And one of the benefits is that the ink, coating, or adhesive, regardless of which one you're using, it's effectively 100% solid. And that means that there's no water-based carrier or solvent carrier that has to be flashed off. The particles that are used in the formulation are very tiny, and so they behave like a liquid even though they're effectively 100% solid. And because what that means is you're not flashing off anything. When it's cured or cross-linked, that process happens very fast, and you get a very complete cure, an instant cure. For inks, it'll give you brighter and bolder colors. For coatings, top coats, you'll get scratch, water, and chemical resistance. There's no VOCs that have to be exhausted out of the building or, burnt and afterburner. So a lot of this is very advantageous to the installation, as well as the benefits that you'll get on your printed product. It increases production speed. You can go quite fast with UV curing. It reduces the needed floor space. These lamps are quite tiny in comparison to a thermal oven or an infrared oven. You can get some really great yields with reduced reject rates because the process is very repeatable and very consistent. And because you're using everything in the ink, coating, or adhesive, there's less waste. Because again, you're not flashing off what you're not using. Everything stays in the tray, so you don't have to remove things when you turn the press off. You can leave it because it's not going to cure unless it's exposed to the UV light. So when we look at the electromagnetic spectrum, which is what you have on the slide in front of you, the electromagnetic spectrum, we measure it in terms of waves. Wave is the distance between peaks, as you see that wave across the bottom of the screen. The visible light, which is what we see, spans between 400 nanometers and 700 nanometers. The UV portion is just to the left, a little bit shorter than the visible light. And that is really what we're focused on when it comes to UV curing. Within that UV spectrum, we break the bands down into UVC, UVB, UVA, and UVV. These are medical classifications that were used when the medical industry started to understand or better understand how light affected the body, whether it burned the skin or caused cancer, how deep it penetrated. So we have adopted those in UV curing just to kind of classify those different wavelengths. So you'll see UVC is trying to pull my pointer up and it's not working. Oh, there it is. So UVC is between 200 and 280 nanometers. UVB is between 280 and 315. And then UVA is between 315 and 400. And these are the primary wavelengths that we use in UV curing. And again, it's just outside of the visible spectrum, which means you can't see UV light. The penetration of these bands varies. UVC tends to be absorbed at the surface. So this is what gives us good surface cure, which makes it not tacky, not greasy. UVB penetrates right below the surface. And then UVA and UVV have a much longer wavelength and therefore penetrate all the way down to the construction, which makes sure that you're getting cure and good adhesion to whatever you're printing on. As I mentioned earlier, there's no real water-based carrier or solvent carrier that has to be flashed off. It doesn't mean there's not water in the formulation. It just means that it's a much more solid solution. You have oligomers, which form the base of the coating or ink or adhesive, followed by monomers that are going to give you some dilution qualities, photoinitiators, which react to the UV light, and then additives, which give you additional processing control, color, pigmentation, defoaming. The key ingredient, though, is that photoinitiator. Without the photoinitiator, the ink coating or adhesive would not react to the light. So what happens is the formulators take these ingredients and they blend them together. Each one of these images within this magnifying glass represents one of those components. The four-sided star is the photoinitiator, which absorbs the UV light and creates free radicals, which transfer energy. And all these particles then combine to form one long continuous chain. And this process, if you're not familiar with it or you haven't seen it, this process is instantaneous and happens as soon as the material is exposed to the UV light. Most UV processes in the industry are used with Mercury Arc Lamps. This is bulb-based technology. You have a Mercury Arc Lamp, which you see at the bottom here, which is a sealed quartz tube with a little bit of mercury inside. When we vaporize that mercury into a plasma gas, it emits broadband UV light. So that UVC, the UVB, the UVA, the UVV, visible, infrared, all of that is part of the spectral output of a Mercury Arc Lamp. There are wires on the end that connect it to power supply. The bulb is mounted in a housing, and there's usually a reflector around the outside of the bulb that directs all of the light to a common focal point, which is where your web or your construction or your substrate is going to pass in front of the system. A microwave lamp is also used in the industry. Many of your converting applications will use microwave lamps. They come in 6 and 10-inch lengths, and you pretty much mount them end to end to get whatever longer length you might need. The mercury bulb is this illustration, this line drawing here at the bottom. It's a sealed quartz tube just like the arc lamp, but there's no wires on the end. Effectively, we're generating microwave energy from these two magnetrons, and as that microwave energy hits the mercury inside this quartz tube, it vaporizes it into a plasma gas and emits UV light. So there's just two different ways of generating ultraviolet energy. Both of them rely on mercury inside a quartz tube, which is very different from LED technology, which is what you see on this screen. So LEDs are semiconductors. They are the products that we are familiar with all of our electronic devices, whether it's smartphones, flat screen TVs, laptops. All of your electronics contain semiconductors, and semiconductors only conduct electricity under certain conditions. This is a schematic of a single LED. On the left, kind of the green area, this is the positive side, or P-type silicon. The right side, kind of the purplish shade, is the negative, or N-type silicon. When these are not connected to an electrical source, nothing happens. They're just in a steady, non-powered state. But when you connect the negative terminal of a power supply to the negative side of the LED, it forces these electrons that normally are trapped on the end or negative side. It forces them and gives them enough energy to jump across this boundary onto the left or P-type side. And when they cross, you see these illustrations of these electrons that have crossed over. When they cross over, they drop into a state of lower energy, and that energy differential comes off as UV light. And so semiconductor engineers will design the various semiconductor products to have different band gap energies between the positive and the negative side. And that is what allows them to produce a red LED, a green LED, a blue LED, or a UV LED. LEDs are grown on wafers, one layer at a time. This is done in a clean room. And it's a lot of vapor deposition and clean room processes that allow thousands of LEDs to be manufactured on a single wafer. And then they are cut off to form the individual LED diodes. So here is a single diode packaged into a device. In this case, the LED is this white portion in the middle. It's about 1 millimeter square, so you can see they're quite tiny. This whole package itself is only about 3.5 millimeters, or 1/8 of an inch on each side. You can see the positive and negative wire bonds, we call them, which is where the electricity comes in. And as that electricity flows to the diode, it emits ultraviolet light. LEDs, as I mentioned, are electronics. When you use them, they will generate both UV light as well as electrical heat. That electrical heat is inefficient. In much the same way you might use your laptop or your smartphone or your tablet, it might get warm to the touch as you're using it because those semiconductors are putting off electrical inefficiencies that show up as heat. For many consumer goods products, there aren't even any fans in products anymore. There was at one time, but a lot of those fans have gone away. UV LEDs will generate heat as well, but we're putting a lot more power into them. So we have to remove that heat just to keep the LEDs at the proper operating temperature. The better we control that temperature, the more stable we keep them, the longer they will last. So in this diagram, you see the electrical energy comes in. Again, it's DC power. It flows across all of our semiconductors. The UV light is emitted in one direction, and then this heat is absorbed into a heat sink and then is removed either through cooling air or liquid water. And again, I showed just some images too. Think of an LED system more comparable to a laptop or a smartphone as opposed to a microwave curing system or an electrode arc lamp system. Again, these are not bulb-based systems. They are true semiconductor LED technology. You can remove that heat either by blowing air. So in this case, all of our LEDs are going to be at the bottom here, below the heat sink. The light is emitted in all of these different directions as it comes out of the light. The heat sink will absorb the inefficiencies, the electrical waste energy, and pull it up these fins. As we blow air across it, it removes that heat and keeps the device cool. Alternatively, we can do this through liquid cooling. The base of the system is the same. You'll have a matrix of diodes, individual LEDs. As they operate, the heat that we do not want is pulled up into the heat sink, and you have a large manifold here, which is basically just a block of metal where cooling water flows through the device to remove and take it away to a chiller, liquid chiller. The semiconductor industry often talks about LEDs in terms of wall plug efficiency. It's the percentage of electrical energy converted into optical power. So if you look at this chart here, which shows years, 1970 to 2020, you can see that the red LEDs, they became quite efficient relatively quick. It was one of the easier LEDs to manufacture, and it's why most of our electronic devices, if they have indicator lights, they were most often red for the longest time. Blue LEDs we started to figure out the material science behind them and around the 90s, and then they've produced what we use for just a lot of our general lighting and high brightness LEDs that we've seen developed in the last 10 years. UV LEDs really didn't start to come on the scene until the late 1990s. They were developed by 3 gentlemen at a university in Japan who ultimately won the Nobel Prize. It was the spin-off of their work on blue LEDs. The scrap that they were generating was actually emitting in the ultraviolet region. And these diodes have increased in output quite rapidly over the last 15 years. UVC is relatively new in terms of LED technology. We're just on this upward trajectory. A lot of coatings cure very well with UVC, and so the next couple of years are really going to bring some innovations and some developments in UVC coatings and other technologies. LEDs are really material science. They we can only manufacture what the material science allows us to create. So material science and manufacturing processes drive what is possible, and then market economics drive what is actually produced. And then finally, the production yield, what we can make on those wafers and what we can extract, as well as what the market is interested in, kind of drive the economics and the price. But ultimately, what's created and is accepted over the long term really is based on the applications. How do we partner that LED output with the chemistry to produce the printed products that we want? So we can make LEDs at just about any wavelength. If you remember that visible spectrum from the earlier slides, this shows wavelengths across the bottom from 250 to 405 nanometers. And we can look at how the market has evolved. In the early years, we were only generating those longer UVAs, 385, 395, 405 nanometers. And as the material science got better, 365 became a popular wavelength, and now we're looking down here on the left towards that UVC output. There's a big difference between the Mercury Arc lamp or the microwave lamp output versus LED. The purple that you see here on the bottom, on the chart, the broad spectrum output is typical of a microwave or a Mercury Arc lamp. It spans the UVC, the UVB, UVA, and the visible. LEDs, on the other hand, are these purple bell curves that have a very high peak irradiance, but only emit in a very narrow part of the spectrum. These next two slides just kind of give you an idea of what LED curing systems look like. They come in a range of sizes, shapes, and form factors. They can be cooled with air or cooled with liquid, and there's lots of different power and controls configurations. The system on the left is a product by GEW. The system on the top right is from Phosion, and then the blue one towards the bottom is AMS, Spectral. So you can see there's a growing range of options in terms of UV curing, and as the nature of each device, depending on who manufactures it and how it's made, kind of dictates how much power comes out. And for very high-speed applications, you might actually need to gang a couple of lamps together to get the speed and the cure for maybe some very high-end or high-speed processes. In this case, we've got 3 lamps that are one right after the other, and the web would pass underneath. So one last slide for me, and then I'll turn it over to Joe to talk about regulatory. All of the benefits for UV curing that I described at the beginning also apply to LED. LED has all the same benefits as conventional curing, but it offers many more. For example, there's no infrared output. To the right of the visible spectrum is where you get the infrared wavelengths. LED is that monochromatic output, so there is no infrared. It's solid-state electronics, so it's instant on, instant off. We get much greater irradiance, much greater power in those UVA wavelengths. Those are the ones that penetrate deep through inks, coatings, and adhesives and substrates. There's no ozone generated by LEDs, so that means no exhaust ducting, which means if you're not dumping air outside your facility, you don't have to bring in conditioned makeup air. There's no mercury, which makes them environmentally safer. And the LED technology, the electronic technology, lasts much longer. You don't have that degradation that you have with a Mercury Arc lamp. A Mercury Arc lamp starts to degrade from the moment you turn it on. So you're constantly replacing those bulbs every 500 to 2,000 hours. With LEDs, you can get much longer life and run for upwards of 20,000 hours without having to change anything in your process or anything in the product. And then certainly just greater reliability and reduced maintenance means more uptime and greater yields. So with that, I will turn it over to Joe to talk about regulation.
Thank you, Jennifer. I'm going to talk about FDA regulation mostly, in that flexible packaging, a large component of that is used in the food packaging market, and how does LED fit within that regulation. I reviewed the 21 CFR, which is the Code of Federal Regulations, which has food contact items listed, and I reviewed FDA's food contact notification inventory, and you won't see LED listed at all. It's not to say that there are components within the 21 CFR that you can't use an LED, but for the most part, we're dealing with a newer technology, and the regulations have not kept up with it. So if you have a component which is not listed and these components could migrate potentially into food, you're looking at a potential adulteration event. I'll speak about that more on the next slide, but an adulteration event is basically anytime you have a component that is not listed and goes into the food, then the FDA would view that as being adulteration. So what can we do to obtain compliance? I'm going to talk about the idea of the concept of a functional barrier or no vibration position. Just briefly on the food contact notification, if you have a product that you want to use in food packaging, you can petition the FDA to review your migration data and risk data, and they will assess that over a period of 120 days, and if they accept the information, they will put your product on their inventory saying, you, company X, can use this product for this end use. It's specific to your company, so there is a benefit to doing a food contact notification. The drawback is it can be a very long process. I'm also going to focus on risk-based approaches to clearing UV LED materials and what's involved in that. So adulteration in food packaging. I think nobody wants to have a recall. Nobody wants to end up on 60 Minutes, so we have to make sure that the food is safe. So chemicals can migrate. What is adulteration then? It's where you can have a chemical that can migrate that potentially cause harm. It could also be if you have something that migrates, which gives an off odor or off taste of the food, so-called, or it changes the organic leptic properties of the food. Or you could have something which should change the composition of food, or it could make it, you know, a yogurt runny, or break down a food product. Something would change actually the physical nature of the food itself. Adulteration also occurs if you have something that migrates which doesn't have pre-market approval. So if it's not listed in 21 CFR, does not have an applicable food contact notification, is above a threshold of regulation, or doesn't have a threshold of regulation determination, which only FDA can do, or doesn't have prior sanction, or isn't generally recognized as safe. If you have a component going into the food, then that is an adulteration event. Any uncleared food additive that ends up in the food is automatically considered an adulteration event by the FDA. You'll see people in the marketplace that when they'll say, oh, you don't have a concern about my product because it's separated from the food by a functional barrier. Manufacturers rely on this frequently. The problem is the idea of a functional barrier is not very well defined. The US FDA only makes mention of it in 21 CFR 175-105. This is an adhesives regulation, so it wouldn't cover things like coatings. It wouldn't cover things like coatings made from UV or LED. And that regulation also requires that you have pre-market approval, so you'd have to have the component listed in 175-105 or GRAS. The EU goes a little bit farther, saying that if you have something behind the functional barrier, anything which is, quote, non-authorized may be used, provided it doesn't migrate at 0.1 milligrams per kilogram, 10 parts per billion, in the food. That's a very low limit. The only guidance the EU and US have given, they both recognize glass and metal as functional barriers, which is a fairly limited area within the marketplace as far as food packaging. The US also recognizes certain types of PET at certain thicknesses that depends on the time and temperature. But overall, there's a lack of description and definition of a functional barrier from the regulation. So what is a functional barrier? If you ask a lawyer, it will most likely say that it prevents all migration. Being that we have fantastic analytical equipment now, the idea of getting to zero is really more of a concept. If you have a good enough analytical technique and it's in there at part per billion levels, we can probably find it today. A lot of people default to a functional barrier saying, okay, if it prevents migration of a substance to 50 parts per billion, then that's safe. That 50 parts per billion level was introduced by the FDA in 1969 and was never formally adopted. Also, toxicology, our understanding around that has increased greatly in the last 50 years. So there are things like carcinogens or reproductive toxins where that 50 part per billion level would not be protective. Other people say a functional barrier prevents dietary exposure of 0.5 parts per billion. This is the so-called FDA threshold regulation. In this case, that's an extremely low level. You have to demonstrate that the material doesn't have a potential for carcinogenicity. So it's not very useful. And the FDA is the only one who can actually make that determination. Others say it depends on the level of the migrating material, the dietary consumption exposure. This is the so-called, what I would say is the risk assessment. My arrow's not working either. Okay, it depends on, okay, there it is. Depends on the level of migrating dietary consumption exposure. This is a so-called risk assessment approach to food safety, where you're understanding what's coming out of the product, you're looking at how the consumers are exposed to that, you're determining exposure, and you're making a risk assessment on that. This is a potential way to clear materials which do not have pre-market approval. The other idea is prevent migration to a dietary level which is generally recognized safe. These two items go hand in hand. If you can demonstrate that your product migrates at a certain level and you've demonstrated their safety below that level, then you can take what I would call a graft approach to that. With the graft approach, the generally recognized safe approach, you have to have data which is publicly available. That's the key to it. If you're able to, I don't want to just go on a tangent here, if you are able to make this determination of safety for your product, I would just say that you comply with you comply with FDA based on risk assessment. A lot of people want to say that they have a functional barrier and therefore they're 175, 105. As I stated earlier, that's specific to adhesives. For that regulation, you have to compositionally comply and have a functional barrier. It doesn't clear non-adhesives, so it won't clear coatings. It won't clear things that aren't listed in 21 CFR under 175, 105. So just a word of caution, if you do take a risk assessment approach, don't go out and try to find a CFR regulation with how you can clear that or how you're going to write your compliance letter. So how do you achieve compliance if you don't have pre-market clearance? Well, one way you can do 100% migration calculations. This generally works. You're going to have to know the residual levels of material in your product, and they should be in a low part per million range. And then there's certain calculations that I'm not going to get into where you look at if 100% is migrated into food, what would the level be within the food? You could also do residual analysis followed by diffusion migration calculations using various software packages. One of them out there is called Migratest. You basically put in the level of material in there, you put your packaging structure in there, you talk about what food types are there, the conditions as far as the temperature, and you can actually come up with what your level would be migrating. You could do migration studies. These tend to be long-term studies, a 10-day extraction, and can require a fair amount of method development. Excuse me. I would use migration studies kind of as the last resort. If you can't get 100% migration calculations or residual analysis with migration calculations to work, I would try, then I would go ahead and do migration studies if you have to. At the end of this, you can't just say, oh, I've had this level come out at this. You have to do a risk assessment at that point. So you have to look at the toxicology of the material, the exposure of the material, and you have to make a safety determination based on the level that was migrating and the level of exposure and the hazard of the material. And the end game is here, we're trying to demonstrate safety of the materials that are migrating. If you are going to get into migration studies, there are many factors to consider. All of them can affect how much a product migrates. The type of food. If you have aqueous or acidic food, it's going to a material come out at X level. If you have fatty food, those tend to cause higher amounts of migration. As you increase the temperature treatment, so if you have a microwavable package or you have a hot fill or the food goes in hot or an ovenable application, you're going to see more migration. The film type is also crucial, and the thickness of that film. And then you may see things where your material is not compatible and may cause with the other materials used in the packaging. So you might have an ink and adhesive together which are incompatible, and they cause one or the other to migrate more highly. If you look at barrier films, generally linear low density polyethylene is a screen door to migration. It's probably one of the worst ones. We use it at Ashland as a worst case screen method, followed by polypropylene, high density polyethylene, and PET. So again, all these are things that you have to consider before conducting a migration test. So you need to understand what your customer is doing with the product, how the package is going to be utilized in the market, and how the consumer is going to use it. So the first question you want to ask is, what types of foods is going into the package? The FDA has broken it down to aqueous and acidic foods, alcoholic foods, fatty foods, and dry foods. And in each one of these, you have a certain food stimulant you have to do your testing in. At present, the FDA has nothing for dry foods. There's no real food stimulant that they recommend. You could probably use 10% ethanol, but again, there's nothing that they recommend because I believe that they don't believe that's a big risk as far as dry foods, but they're now looking at it and they're going to talk about possibly releasing some new stimulants that you might have to use, like 10X. For aqueous foods and alcoholic foods, the food stimulant you'd want to use is 10% ethanol for your migration studies. For fatty foods, the FDA recommends these food oils. The problem is that they're very difficult to analyze, so they will accept 95% ethanol as the food stimulant. So what are the effects of the food stimulants on migration? In this slide, this is not an LED material. This is a material that was used in a laminating adhesive. It's an aromatic isocyanate, and I'm demonstrating the migration of aromatic isocyanate in a fatty food stimulant, which is 95% ethanol, and an aqueous food stimulant, which is 3% acetic acid. Cure time, which is not relevant for LED, you actually have to cure these things over time for the laminating adhesives. But what you can see clearly is that in aqueous food stimulant, you have much lower migration than compared to a fatty food stimulant. The key thing to hear is if you're doing a test in acetic acid or 10% ethanol and you're packaging cheese, let's say, or some other fatty food, you're probably underestimating the amount of migration that's going to occur, and you'd be underestimating the risk. Temperature is also critical for migration testing. The FDA has multiple conditions of use. You have conditions of use A through J. A is for high temperature retort. And as you go down, the conditions become a little less severe. Condition of use E is for room temperature. At that testing, you would test a product for 10 days at 40 degrees Celsius. If you had a product which you wanted to do a microwave test to see if it could be microwaved, if it was a frozen food or refrigerated food, you could use condition of use H, which is 2 hours at 100 degrees Celsius. But again, you want to match your conditions of use to how the food is going to be used. And then here at the bottom, you have cooking temperatures. Basically, anything above 121 degrees Celsius. The FDA recommends that you use the product, or you test the product at the temperature the food is going to be exposed to and for the duration. So if you have something that's at 350 degrees Fahrenheit for 2 hours, you would test at that. So what are the effects on time and temperature? So again, this is an aromatic isocyanate migration from a laminating adhesive on it has a 3 mil linear low density barrier film. All this testing was done in 95% ethanol, so this is a fatty food condition, so I want to keep the conditions the same. You see at room temperature, there's less migration, but as you go to FDA conditional use H, so this is your kind of like your frozen burrito application where you have a refrigerated or frozen food and you throw it in the microwave, you can see migration increases. But then if you go to this next, which is conditional use B, this is 2 hours at 40 degrees Celsius, so this is boiling water sterilized. You can see the migration does increase because it's the combination of both the high temperature, which was 100 here and 100 here, and the shelf life, because there's an additional 10 days at 40 degrees Celsius. So again, just be cautious of how you set up these tests. So once you do your testing, what are you looking for? You want to, before you even do your testing, you want to establish a safe dietary level using the hazard information on the chemical of interest. So you're going to go through the tox data. You're going to say, okay, I have chemical X. It has this toxicity. The population is going to be exposed at 5%. Therefore, I can establish a dietary level, or excuse me, I can establish a dietary level based on that information. Then you would set your, excuse me. So in FDA's toxicology guidelines, there's a list of the minimum data required. So if you have something that migrates really low at 0.5 parts per billion or less, you don't have any data at all that's required. As long as it's not genotoxic, I mean, if you don't have to have any data. From 0.5 to 50 parts per billion, here you would have to have 2 in vitro genotoxicity tests. And at 50 parts per billion to 1 part per million, you'd have to have the genotoxicity test and 2 subchronic tests, which are 2 90-day tests in mammals. Those are quite expensive to run, so if it's not publicly available, it could be very expensive to do this. So you would have, so between establishing you get the hazard information from the toxic data, you find the exposure, and the FDA has guidance out there as far as how you would look at exposure based on the type of packaging. They're called consumption factors. Between those two, you could determine the risk of the material. So using these principles, Ashland actually took an LED product, 2 of them, and wanted to determine the migration of them. So we actually did migration testing, and we were able to clear 2 materials. One was a cure dose of equal to greater than an amount of 300 feet per minute, 100% power, 20 watts per centimeter squared at 395 nanometers. This passed condition of UC, which is a hot fill condition, and would go all the way down to frozen food storage. This required a 2 mil polyethylene film, linear low density polyethylene. If it were less than that, then we'd have to repeat the test. And here's the coat weight for the material. Another one that we've cleared recently, dose equal to 500 feet per minute, 100% power, 16 watts per centimeter squared at 395 nanometers. This was a thicker barrier, 3 mil, and again, we could not get to that condition of UC. We were only able to clear it for condition of UC, which is room temperature. So again, conditions are important. You can't just say I've cleared at this level and therefore you can use it in all these applications. You really need to do your homework on this. And I think that's my last slide.
I think it is. So I will pick back up from here and kind of talk about some trends. And then I'm going to tie it all together. I'm going to give you a little more information on LED technology and why it's something that you should be paying attention to. If we look at the growth in the flexible packaging market in the U.S., you can see on this graph here on the left that from 2000 to 2017, so the past 17, 18 years, the U.S. market alone, it's grown from 19 billion to 31 billion. So it is an upward trajectory, and it's primarily because of the convenience of flexible packaging, the lighter weight of flexible packaging. As we move to an e-commerce market, it's easier to ship flexible packaging than rigid packaging. And so much of what Joe was talking about is important because when you have rigid packaging, you have a more formidable barrier, whether it's glass or a higher density plastic. And whenever you're producing or filling with a food product, whether it's for human consumption or pet consumption, and even if it's a product not for consumption, we just don't want any of the materials in the ink, coating, or adhesive to end up inside that package. And so that's why it's important to understand what the regulatory landscape is, so that we can make sure that we're producing what the market wants, but also safely. So the second chart shows that as we look at all of the market segments, and these charts are from, you can see where the source is here at the bottom, but this chart is from 2017, and it's the U.S. packaging market by segment. And you can see that of all the segments looked at, you know, flexible packaging is about 19% of the composition, only slightly behind corrugated. I mean, corrugated packaging has been used, you know, for decades and has always been, you know, one of the, you know, the largest printed material. But flexible packaging is making, you know, quite a bit of inroads into that space, and it's something to pay attention to. This last slide kind of segments a little bit differently. It's more by type as opposed to market. But even in this breakdown, again, compared to glass, liquid cartons, metal, paper-based containers, and then rigid plastic, flexible packaging, even by 2017, is almost 40% of that market share. So this is a trend that's going to continue. We're going to see more and more products moving from rigid packaging to flexible packaging. And a lot of that is because, you know, the market likes the convenience of flexible packaging, whether it's single serve or larger product serve or resealable. We like that flexibility. We like that convenience. So we're looking for high performance film, retail ready packaging. We want things to be, you know, recyclable and biodegradable. And then that e-commerce is a big part of what's driving this. It's just easier, more cost effective to ship flexible packaging than rigid packaging. So what does all this have to do with LED? I started this presentation by just kind of giving you a little bit of insight as to how LEDs are made, you know, what a lamp looks like, what the output is, how it's different from conventional mercury-based bulbs. Well, probably the biggest takeaway that I'd like you to leave with after this webinar is that existing LED curable formulations are safe for use in flexible packaging, and that includes inks, laminating adhesives, and coatings. Now, formulations from all suppliers are not equal, so you need to be, if there's a space that you're working in or a space that you're investigating, you need to make sure that you're working with formulators that have experience with LED technology, experience with UV technology, because there are solutions that are safe. There's solutions that are being used today, and so it's something that you should be considering for your flexible packaging applications. A lot of this work has been done in the narrow web space. It was easier, you know, to kind of develop applications in narrow web at slower speeds and narrower widths. And now that we've got a large portfolio of solutions, and if you watched the other webinar that was last month, either in the archives or maybe you sat in on it, you can see where we've gotten success and what's working today. And now we're scaling that up. As the flexible packaging market grows, we're taking what we're learning in narrow web and expanding it to mid-web and wide web. And historically, a lot of mid-web and wide web has not been UV at all. So even the Mercury, you know, arc lamp and microwave lamps haven't played a big role in flexible packaging. You know, the space is tighter on a central impression press. You know, water-based formulations have often been used. So LED, by its compact nature, the discreteness of its output, the sustainability factor, and really just the uniqueness of its output compared to water-based and solvent-based that have to be flashed off with a thermal dryer or conventional UV, there's going to be an increase in innovation just because it allows us to do very interesting things with inks, coatings, and adhesives that we can't with other drying mechanisms. So LED advancements, why mid-web and wide web is starting to make more sense is the LED systems are getting wider. You know, we're not talking about the early days when we were doing, you know, 75 millimeters or 3 inches in a digital inkjet application. You know, we can now do 126 inches in a single wide, long lamp. They're more reliable. The pricing has come down. They're much more economical. They have low profile form factors that can fit into tighter spaces on existing printing presses. And they're more powerful. So we need power to achieve the speeds that mid and wide web run at. And so as the lamps have become more efficient, as we've been able to generate more output, And as the pricing has come down, where maybe we want to use 2 lamps or 3 lamps to get increasingly higher speeds, that's now a viable option. The short UVC LED wavelengths that are probably going to be commercial, within the next 3 to 5 years, they're going to open up a whole nother realm of coatings technology that we haven't really even begun to explore yet. And then the sustainability benefits, not so much, I'm not talking so much on recyclability, I'm talking more on process, your manufacturing process. And I'll talk about that next slide, but that's very important to brands and converters. So here we are, sustainability. Much of the LED sustainability story has to do with the production setup. So for example, if you remember to those early slides, UV LED systems do not emit any infrared output or visible output. Your conventional mercury lamps do. So conventional UV emits all sorts of bandwidths that the chemistry does not use. LED eliminates that. It's a much more precise curing solution because what's emitting is what the chemistry is tuned to react to. They also don't emit the type of output that your thermal dryers, your hot air dryers, a lot of that energy, some of it you can use to flash off the water or the solvent, but a lot of it just becomes wasted. You're heating up that entire enclosure. It's coming off into the plant. That all goes away. There's no mercury in an LED system. We talked about how there's no ozone generation, so you're not putting holes in the roof of your facility. You're not having to dump in additional makeup air that has to be air conditioned in the summer or heated in the winter if you happen to be in a climate-controlled facility. There's solvent-free formulations, and what I mean by that is there's no solvent carrier. They're low to near zero VOCs, which means you don't need afterburners. And that instant cure and that faster processing means that when you have product that comes off that line, you can post-process it immediately, either fill it, do what you need to do with your internal processes, or get it out the door and ship it to your customer. So that warehousing, that racking, that 1 to 7 day post-cure drying time that you need, that all goes away. So LED makes your process faster, more efficient, takes up less space, and you get consistent UV output across the life of the product, provided the LED system was engineered correctly. This is a hot market right now, and there's a lot of suppliers coming into this industry. And you have to take a look at who those vendors are, and not all products are the same. LED is viable, it works, and it's sustainable. But that doesn't mean that every single product on the market fits that bill. They are very efficient systems. They still generate that electrical waste energy, but again, that's the same thing that our laptops and our smartphones and our flat screen TVs are doing. So as long as we manage that electrical optical energy that's coming off, the amount of wattage that's going into the lamp is much less than what a mercury lamp would be or a thermal dryer would be. And then in terms of low migration, the reason LED is such a good partner for low migration, and we're really just starting to get into this space. Joe showed you slides that show the laminating adhesive. Ashland has done testing that shows that laminating adhesives are incredibly safe, for flexible packaging applications. But the key takeaway from that is that when you use an LED laminating adhesive, as soon as that product comes off the press, you can immediately slit it, form it, fill it, and seal it. You can't do that with other curing technologies. For those of you in this space already, you often have to store those rolls anywhere from 1 to 7 days. You may be able to slit it after a day or two, but you can't fill it sometimes for 5, 6, or 7 days. So think about how that impacts your operations, your processing time, your ability to deliver product to customers. All of that is incredibly important and a big part of the ROI with LED technology. So even though some of the formulations, if you talk to your suppliers, if you talk to Ashland, you might start comparing an LED adhesive, an LED coating, or an LED ink to what you might be using today that's water-based or maybe solvent-based or solvent-free. You might get, you might look at those prices and say, well, I can't justify that. I'm just looking at the price of one versus the other, and they're not the same. because you don't have all of that carrier in there that has to be flashed off. And if you look at the whole cost analysis, the increased throughput and the ability to ship product, right off the press really starts to make that ROI look incredibly attractive. And then the nature of that LED output, the fact that it's a very intense. I mean, think about looking at an LED flashlight or an oncoming car with LED headlights. It's very bright. That high brightness, longer wavelength LED penetrates through inks, coatings, adhesives, and films much better. So what that means is your substrate selection starts to open up, because if you're trying to cure through something, you've got more options with LED. If you have thicker coatings or adhesives, that longer white allows you to cure through, all the way through that ink coating adhesive and bond to your, give you really good adhesion to your construction. And if you're using ink, that longer wavelength also is very helpful and beneficial when you have heavily pigmented and dense inks. So again, you're going to get brighter, bolder colors. You're going to get, haptic and tactile and coatings with UV technology that you don't necessarily get with water-based or solvent or solvent-free. And you get better process control. Consistent UV LED output over time for much longer periods means that's one variable on your press that goes away. Periodically you're going to have to look at it just to make sure that it's working correctly, but it's not degrading as a Mercury Arc or a microwave lamp would be. So it's one aspect that you can rely on, every hour of every shift, across the week, across the month, across the year. And because there's fewer variables to monitor, it just makes your maintenance team and your operators' lives a little bit easier, because they're not having to constantly address a potential curing issue. Some of the things that Joe talked about in his slides, the LED all of a sudden, if it's partnered and matched correctly to the press and the application, it's less of a concern for your overall process. And then finally, one thing I didn't get into too much, but it's talked a little bit more on the other webinar and maybe other presentations I've given, is that with conventional UV, the wavelength, which is that UVA, UVB, UVC, the irradiance, which is that peak power, and then the total energy. With conventional UV, those three things are wrapped up together tightly. You can't separate them. LED allows us to pull these apart discreetly and start to explore how that affects the chemistry. And that is what's going to allow us to be innovative and come up with very unique and innovative things for packaging that you can't do with water-based or solvent-based or solvent-free or even conventional UV. So flexible packaging is growing like it's predicted to continue growing. And brands are continually interested in how to differentiate their product line and make their product stand out on the shelf. LED is going to be a big part of this going forward. And now, because of the compact form factors, we can fit these on presses that we couldn't fit UV on in the past. So final slide, summary slides, and we'll open it up for questions. Flexible packaging is one of the fastest growing market segments in packaging. For those of you in this space, you already know this. With LED, it's an increasingly viable option for mid and wide web presses, and that's because the power has gotten better, the lengths have gotten wider, the form factors are more low profile to fit on the various presses, and the UV LED curable formulations already exist today. They're safe and they're being used in flexible packaging, predominantly in the narrow web space. And so what we're looking at is how do we shift that into the mid space, the mid web space, and even the wide web space. And that better process control from LED output, that's what's going to help address all of the regulatory concerns in Joe's slides. If you have a very stable curing mechanism that you can rely on, that's consistent, that's sustainable, it will help ensure that the product that you're producing is suitable for low migration, or often, I think we're now starting to call it FCM, which is food contact materials. You might start to hear that word a bit more, but LED is a good fit. So understanding and navigating that regulatory landscape that Joe talked about is essential for good manufacturing practices. But it's not something that should be overly daunting. It's just something that you have to educate yourself on. It's something that you have to be aware of. You know, there are lots of us in the industry that operate in a space that are certainly here to help. And then once those good practices, those good manufacturing practices are put in place, then you have a stable, repeatable process. But LED in general, it positively impacts sustainable manufacturing processes because it does consume less energy, it takes up less space, and most importantly, it allows you to get product out the door in a much shorter time period than any other drying technology you may be using today. So with that, we will open the floor up for questions.
Thank you, Jennifer, and thank you, Joe. I know we're at 3 o'clock. We probably can take a few questions, and you can always follow up with Jennifer and Joe. Their contact information is right there, but if you want to just type your question into the Q&A window, they'll try to answer it. And while people are thinking, just a reminder again, the RadTech conference is coming up in March, radtech2020.com for more information or to sign up.
So we either have an audience that fell asleep somewhere during our presentation, or we've just answered all of your questions. I know this is a relatively new space. I know LED technology may be new to many of you. UV technology may be new to you. So if you're not coming to any questions that you might want to today, then by all means, feel free to reach out to us at a later date. So here was one question that popped up. Can you cure through opaque? So one of the huge, better advantages or the LED technology offers is because the wavelengths are longer, they're in that UVA region that's closer to the visible. Those longer wavelengths from the earlier slides in the presentation, they actually penetrate all the way through. So what that means is when you have opaque formulations, whether it's an ink, a coating, or adhesive, if there's some sort of an additive in there, typically what those additives do is they either block, reflect, or scatter the light. Well, many of the longer wavelengths don't get absorbed by those additives. So LED actually enables greater opacity, so white, heavily pigmented blacks, curing through films that might have a cloudiness to them, curing through foils. LED is much better for that. So the answer to can you cure through opaque with LED, the answer is yes. And I think that might be it. Not a big question webinar, but that's okay. The slide materials are there for your review, and you have our details if you want to reach back out to us later.
And just a reminder again, everybody, this webinar, along with the UV narrow web webinar, are available on the archive site. You'll get an email after this is over, just reminding you where that web address is. And generally it takes about a day or two for our web person to get the new presentation archive up there, but it'll be up there fairly soon. So I'd like to thank Jennifer and Joe again for your time and expertise in this area. UV LED is always one of the really popular webinars that we do as part of this series. So thank you both again, and I hope everybody has a good afternoon.
Thank you, Brandon.
Thank you. Take care.